Quantitative variables are variables measured on a numeric scale. Height, weight, temperature, and scores on an exam are all examples of quantitative variables. Quantitative variables are distinguished from categorical variables, such as favorite color, religion, city of birth, and favorite sport, in which there is no ordering or measuring involved. Categorical variables are sometimes called qualitative variables. There are many types of graphs that can be used to portray distributions of quantitative variables, and the upcoming sections cover several of these. Some graph types, like this stem and leaf graph, are best suited for small to moderate amounts of data, whereas others, like this histogram, are best suited for large amounts of data. Some types of graphs are good at summarizing differences between distributions. These two box plots compare the time to complete a task for men and women, while others, like the scatter plot, are used to show the relationship between variables. A stem and leaf display is a graphical method of displaying data. It is particularly useful when your data are not too numerous. In this section, we will explain how to construct and interpret this kind of graph. As usual, an example will get us started. The top of the display shows the number of touchdown passes thrown by each of the 31 teams in the National Football League in the 2000 season. A stem and leaf display of the data is shown below. The left portion of the stem and leaf display contains the stems. They are the numbers 3, 2, 1, and 0 arranged as a column to the left of the bars. Think of these numbers as tens digits. A stem of 3, for example, can be used to represent the tens digit of any of the numbers from 30 to 39. The numbers to the right of the bar are leaves, and they represent the ones digits. Every leaf in the graph therefore stands for the result of adding the leaf to 10 times its stem. To make this clear, let's examine the display more closely. In the top row, the 4 leaves to the right of the stem 3 are 2, 3, 3, and 7. Combined with the stem of 3, these leaves represent the numbers 32, 33, 33, and 37, which are the number of touchdown passes for the first 4 teams. The second row has a stem of 2 and contains 12 leaves. Together, they represent 12 data points, namely 2 occurrences of 20 touchdown passes, 3 occurrences of 21 touchdown passes, 3 occurrences of 22 touchdown passes, 1 occurrence of 23 touchdown passes, 2 occurrences of 28 touchdown passes, and 1 occurrence of 29 touchdown passes. I will leave it to you to figure out what the third row represents. The fourth row has a stem of 0 and 2 leaves. It stands for the last 2 entries in the data, namely 9 touchdown passes and 6 touchdown passes. The latter 2 numbers may be thought of as 09 and 06. One purpose of a stem and leaf display is to clarify the shape of the distribution. You can see many facts about touchdown passes more easily in the stem and leaf display than from the raw numbers. For example, by looking at the stems and the shape of the plot, you can tell that most of the teams had between 10 and 29 passing touchdowns, with a few having more and a few having less. The precise numbers of touchdown passes can be determined by examining the leaves. We can make our figure even more revealing by splitting each stem into 2 parts. The display on the right shows how to do this. The top row is reserved for numbers from 35 to 39 and holds only the 37 touchdown passes. The second row is reserved for the numbers from 30 to 34 and holds the 32, 33, and 33 touchdown passes made by the next 3 teams. You can see for yourself what the other rows represent. The figure on the right is more revealing than the figure on the left because the latter figure lumps too many values into a single row. Whether you should split stems in a display depends on the exact form of your data. If rows get too long with single stems, you might try splitting them into 2 or more parts. There is a variation of stem and leaf displays that is useful for comparing distributions. The 2 distributions are placed back to back along a common column of stems. The result is a back-to-back stem and leaf graph. Here you see such a graph. It compares the numbers of touchdown passes in the 1998 and 2000 seasons. The stems are in the middle, the leaves to the left are for the 1998 data, and the leaves to the right are for the 2000 data. For example, the second to last row shows that in 1998 there were teams with 11, 12, and 13 touchdown passes, and in 2000 there were 2 teams with 12 and 3 teams with 14 touchdown passes. There are 2 things about the football data that make them easy to graph with stems and leaves. First, the data are limited to whole numbers that can be represented with a 1-digit stem and a 1-digit leaf. Second, all the numbers are positive. If the data include numbers with 3 or more digits or contain decimals, they can be rounded to 2-digit accuracy. The data shown here are from a study on aggressive thinking. Each value is the mean difference over a series of trials between the time it took an experimental subject to name aggressive words, like punch, under 2 conditions. In one condition, the words were preceded by a non-weapon word, such as bug. In the second condition, the same words were preceded by a weapon word, such as gun or knife. The issue addressed by the experiment was whether a preceding weapon word would speed up or prime pronunciation of the aggressive word compared to a non-weapon priming word. A positive difference implies greater priming of the aggressive word by the weapon word. Negative differences imply that the priming by the weapon word was less than for a neutral word. You see that the numbers range from 43.2 to negative 27.4. The first value indicates that one subject was 43.2 milliseconds faster pronouncing aggressive words when they were preceded by weapon words than when preceded by neutral words. The value negative 27.4 indicates that another subject was 27.4 milliseconds slower pronouncing aggressive words when they were preceded by weapon words. The data are displayed with stems and leaves in the lower right. Since stem and leaf displays can only portray 2 whole digits, one for the stem and one for the leaf, the numbers are first rounded. Thus, the value 43.2 is rounded to 43 and represented with a stem of 4 and a leaf of 3. Similarly, 42.9 is rounded to 43. To represent negative numbers, we simply use negative stems. For example, the bottom row of the figure represents the number negative 27. The second to last row represents the numbers negative 10, negative 10, negative 15, etc. Observe that the figure contains a row headed by 0 and another headed by negative 0. The stem of 0 is for numbers between 0 and 9, whereas the stem of negative 0 is for numbers between 0 and negative 9. For example, the fifth row of the table holds the numbers 1, 2, 4, 5, 5, 8, and 9, and the sixth row holds 0, negative 6, negative 7, and negative 9. Values that are exactly 0 before rounding should be split as evenly as possible between the 0 and negative 0 rows. Although stem and leaf displays are unwieldy for large datasets, they are often useful for datasets with up to 200 observations. This stem and leaf display portrays the distribution of populations of 185 U.S. cities in 1998. To be included, a city had to have between 100,000 and 500,000 residents. Since a stem and leaf plot shows only 2-place accuracy, we had to round the numbers to the nearest 10,000. For example, the largest number, 493,559, was rounded to 490,000 and then plotted with a stem of 4 and a leaf of 9. The fourth highest number, 463,201, was rounded to 460,000 and plotted with a stem of 4 and a leaf of 6. Thus, the stems represent units of 100,000 and the leaves represent units of 10,000. Notice that each stem value is split into 5 parts: 0 to 1, 2 to 3, 4 to 5, 6 to 7, and 8 to 9. Whether your data can be suitably represented by a stem and leaf graph depends on whether they can be rounded without loss of important information. Also, their extreme values must fit into 2 successive digits, as the previous data fit into the 10,000 and 100,000 places for leaves and stems respectively. Deciding what kind of graph is best suited to displaying your data thus requires good judgment. Statistics is not just recipes.